All right, I guess we'll go ahead and start. My name is Brendan Donahe. So I'm probably most well known in the CoCo community for being one of the creators of CoCo VGA, the VGA adapter for CoCo 1 and 2, MT10 Dragon, things of that nature, devices with a 6847 VDG in them. Anyway, what I'm going to be talking about here is how to expand disk extended color basic for the CoCo 1 and 2 and add more commands to it. And so, although the purpose of me doing this this project, or mini project, was to give folks extra commands under basic for CoCo VGA, I think it's applicable to anybody who would like to add more instructions, for example, to basic. So let's start with, well, why basic? Why do we care? There are arguably more powerful operating systems out there for 6809 systems. Well, first of all, it's in ROM on all CoCos. You turn it on, it's there, it's presented to you. Assuming you don't have a cartridge installed, of course. It's a much more, in this case, it's a very common request from CoCo VGA users. Hey, can I get access to some of the enhanced features without, struggling with pokes and things like that? And, last but not least, well, Microsoft Basic kind of lends itself to further enhancement. So anyway, with that, let's start by talking about the disk extended color basic memory map. So this actually applies to both a 32K system and a 64K system, although I would be speaking, very shortly about and focusing on 64K systems. Anyway, the lower 32K up here, 0 to 7FFF, right? That's a RAM region, right? It's used by BASIC. It's used by the user for their own code, stack space, things like that. The upper, which is shown here on the lower part of the table, is Rom registers and a little bit of unused space, right? So notice that up at the very bottom of memory, there's some basic system RAM there, and includes some hooks and some jump table players. So we'll be coming back to that here very shortly. So this is a very heavily edited excerpt from the Basic Unraveled book series. So kind of notice that there's 4 sets of tables mentioned here. These RMB, hopefully you can read that from back there at the back, set aside bytes for 4 different tables in this case, or 4 different pairs of tables actually. So Color Basic has 10 bytes described above at offset 120 hex. Extended Color Basic 10 bytes later at 12A. Disk Basic at 134, and then user space and expansion space at 13E. So I've sort of taken the liberty here of kind of striking out things that don't interest me for the purposes of what I'm doing here. So, so the first half of this, the first 5 bytes, are specifically for the for commands, and the second 5 bytes in each of these is for functions. So I'm not adding any functions. I'm not interested in adding any functions, right? Functions are, they return a value, right? I'm interested in adding commands. I'm just sending information to the hardware. So I'm only interested in this part. But let's walk through these just a little bit. So first of all, the number of reserved words is the first byte in here. It so happens that BASIC's table starts at token number hex 80, and there are 53 reserved words. Add that up, you get B5. B5 plus the 25 from extended BASIC gives you CE. CE plus the number of commands in disk BASIC gives you hex E1. So that means that any of the commands that are added, that I'm adding, will start after token E1. So we'll talk a little bit more about the tokenization stuff. It's kind of like, well, okay, so we've got the number of reserved words. What are these other two pointers, right? You can see that these are 2-byte values. So these are 16-bit addresses. The first one is a lookup table into strings, right? So we're going to be able to match up the strings and say, oh, that's going to be this token number. We'll talk about that a little bit more in a second. And the second one, well, it just depends on whether it's color basic. Color basic has a pointer to a jump table, but all the other ones are pointers to a command handler. So that command handler will use a table, but it will return an index, pointers, things like that. We'll talk about that more. Anyway, and the whole idea here is that any table that doesn't exist is intended to be, zeros, right? So it sort of terminates the list of tables. So BASIC automatically knows to walk through these, right? If it finds that there's a token, the token it's looking for is not in the basics table, it falls through to the extended basics table. If it's not there, it falls through to disk basic. If it's not there, it falls through to, well, an empty region that says syntax error. It doesn't know what you're talking about. Anyway, feel free to stop me if there are any questions or confusion. This is reasonably deep. Okay, so let's talk a little bit more about, why are there two tables? So the first is for the tokenizer, right? It's going to look at all these strings, and it's going to turn them into token numbers. So that has advantages, right? I mean, if you can turn these long strings that are human readable into 1-byte values, it saves a lot of memory, right? Secondly, it speeds things up later. If you don't have to, your interpreter's already slow. If you don't have to do a string comparison to decide what to do next, and use a jump table instead, it can speed things up a lot. So that second pointer, like I said, is intended to go through an interpreter that then looks at the jump tables, or walks through the jump table and provides that address. So, let's see here. So here are the 8 commands that I'm adding. And I'm not going to go through the code for all of them. There's too much to talk about. But I am going to describe some of the setup for them and some examples for how to deal with some numeric integer values, because that's all I needed. Okay, so 2 tables. You'll notice they're sort of parallel tables. So I'm setting aside these strings for doing the comparison. So you enter your line of code, and the interpreter walks through and converts what you've typed into a token, right, a byte value. And then later on, when your interpreter executes your command, it walks through this jump table and uses the indices that you figured out were your token as an offset into this table, right? And you'll see these are double bytes, so these are each 16-bit address. Okay, so here's that tokenized dispatch. So in this case, I'm adding 8 commands. The highest token I'm starting from is E1, right? This is the end of disk extended color basic. So first, let's compare and make sure that we're not looking at a token that's beyond the range of what we can compute. If it is, okay, unrecognized token, syntax error, right? Jump back into the ROM. If it's a good command, it's within range, then we're going to grab the address of that jump table I just showed, top of the jump table, and we're going to, let's see here, subtract off this offset so that we can index into that, and we'll now have that in X, and we'll jump back into the ROM. The ROM will invoke that function for us. Okay, so now this is so slight change of gears, right? Everything up until now has been 6809 assembly. I happen to write my loader in C. CMOC is a comfort zone for me. So I told it I'm adding 8 commands. I want my table of strings to be at E100. I want my interpreter, which was that function we just talked about, right here, to be at EE86. And then I'm going to overwrite 13E. If you guys remember, 13E was right here, this 10-byte user space command interpretation table. So I'm going to overwrite that. I'm going to grab that, use that as a pointer here. I'm going to write byte 0 is the number of commands, 8. Bytes 2 and 3 are the address to the string table. Bytes 3 and 4 are the address of the interpreter we saw on the previous slide. And then I don't have any functions, so no new functions. And I'm going to terminate my list. No more tables. All right. Okay, so you may have already noticed I mentioned doing all these things at EE100. It's like, well, wait a minute. That's unused space. That's ROM, right? You can't do anything there. Well, so what I'm doing is on a 64K machine, I can turn this into RAM and put that stuff up there. So it just so happens that that's very convenient for us because, you know, stock basic on the CoCo only uses this region, and it doesn't know anything about this. So this is a really good place to stick this stuff that I want to put there. It doesn't know any better. So I think there's actually some projects out there that I think Tim Lindner's Squanchy Basic actually moves this stuff up and grows this region. So that's an option too, but not the way I was attacking it. Let's see here. Okay, so, how do we get to this? How do we turn it into RAM? So this is where the SAM comes in. So we can remap that upper 32K into RAM. To do that, what we need to do is you can write to a particular address, and that tells the SAM to switch between 32K split between RAM and ROM, or all 64K RAM. So here's a routine that I stole a number of years ago from Alan Huffman's website, and I disassembled it and kind of reverse engineered it for my own use. But basically, it starts by copying 6 bytes at a time, and then you can see that as it's doing this, it's writing to FFDE and FFDF, right? Those two locations that we talked about for switching the SAM back and forth between 3232 and 64K RAM mode. And so we put it in, make the ROM appear, we read in 6 bytes, we make a RAM appear, we write it into the RAM, right? So once we've iterated over all this, we start out with multiples of 6 bytes, and then we have to finish it up with 2 bytes. There's other algorithms for this. There are simpler ones. There are probably ones that are faster. There are definitely ones that are simpler and slower. But anyway, kind of gets the point across. So at this point, we've switched back and forth a bunch of times between RAM and ROM in that upper space, and we've copied what was in ROM into RAM. So now we can execute out of RAM, right? So the BASIC doesn't know that that upper region has been changed out from under it, or is now RAM, but it still looks the same to it. Okay, so now we need to step back just a little bit and talk about how, some of the underlying features, how CoCo VGA works under the covers, just so that some of these other things that I'm going to talk about make a little more sense. So I don't have the code for this in here. If there's desire for this information, it's on the website, or I'm happy to share it with you. But the important takeaway is that we need our machine language routines in this upper memory, but we also need a shadow memory region. So there's no way to read information from, there's a limited number of pins on the 6847. And so the way I get it into enhanced modes is during the blanking region, I twiddle the 5 pins, the 5 mode bits on the VDG. Then CoCo VGA says, oh, that's a special combo lock that's meaningful to it, so that it sort of acts like a DMA engine and streams in the next video page as data, as configuration settings for itself, and just displays the old frame for one more frame. So, so anyway, just a little bit of background and why I'll be setting aside some RAM regions for streaming, and they need to be 512 byte aligned to work with the SAM, but why I'm setting aside some of these regions for compatibility with it. Okay, so based on the information about the memory map and about how CoCo VGA works, we can slice up that region that we talked about, the E1000 to FEFF region, into these three regions. So character set load region, we won't be talking about that anymore. So here's the kind of the main configuration page. And then we have room for, the basic extension itself, right? All the things that we talked about from E100 and up for tables, code, and data. So this is an example of the 512 byte region at EC100 there. This is kind of what it looks like byte by byte as you walk down individual bits, and how you talk to CoCo VGA by filling this out and then sending it to it. So by having this sort of, laying around in memory as a shadow copy of what configuration has been uploaded to CoCo VGA, it gives us the ability to retain state when we can't read the state back out of CoCo VGA as well. Okay. All right, so bit of an eye chart. So this is another table that belongs in the EE100 to FEFF region. So I don't know if any of you guys were at the 2017 Tandy Assembly presentation where I patched BASIC to basically make it so we could use the 64-column text mode in it. But I distilled that down to 32 bytes of patch, just kind of sprinkled around in various places of color basic and extended color basic. It fixes up set reset, it fixes print and print at, the cassette load status that appears in the top left corner, and things like that to work in a 64-column text mode. So you'll see that there's address data pairs. Actually, they're tuples, address data data. And so the address is the location in ROM that's now RAM that will need to get patched, along with a byte that we would need to stuff at each of those locations for the patch for 64-column mode, and a byte that we might use to go back to 32-column mode, right? Because we need to unpatch the ROM, so to speak, if we want to switch back and forth between 64-column text mode and 32-column text mode. So anyway, so you'll see that not only do we have an address that we're patching, but we also set aside 2 bytes for one for the 64-column patch and one to come back to the 32, which is not in there yet. Okay, so this is an init routine that's called by the C code loader. So it sets some global variables just kind of regarding system state, makes some assumptions about what state we're in. That would be something I'd probably need to fix in the future. And it copies those 32-column values, right, out of the ROM, or now RAM, into this table so that we can unpatch later like I talked about. And it also clears out that shadow register page so that it's all initialized with some sort of set of defaults. And so let's talk about vReset real quick. So this one, thankfully, is a very simple routine, right? So this is vReset. This is, the first command that I added. So not only does it switch us back into 32-column mode, but it also, let's see, and redoes the initialization of globals and things like that, but it also takes and writes an FF to CCV regadder. If you recall, that is simply the top byte. So by writing FF, all ones into offset 0 there, it resets CoCo VGA to factory defaults. Oops, went too far. So, and then we call the function that, like I said, I described but didn't show here, that basically takes these settings, uploads them to CoCo VGA resets itself, while it's doing so, shows the previous video frame, and then we clear this, this guy back out so he's 0 again. So that's all I needed to do to add the vReset function, right? I mean, granted there's some subroutine calls in there, but anyway. So then scanline. So this one's a little bit more interesting because it takes one argument. So you'll notice that up here, B&E, it uses the Z flag. So BASIC will have the Z flag set if there are any options, any arguments to any of the commands that show up after your command. And so if none are present, well, we jump back into the ROM with an error. But if there is one present, then we call into the ROM to actually parse it for us. So let's see here. This get byte argb grabs the next argument for us from, token followed by argument, grabs that argument, puts it into register B, and and then it does the translation to put it in the right place into that shadow memory, and then uploads it to CoCo VGA. So this is the entire function needed for turning on the scan lines. And then vpalette is the command that takes the most arguments. It takes 5, and they're comma separated. So we call into the basic parser to not only, well, check that any exist, first of all, but then we also, we can consume the commas that appear and then, grab the next numeric value. So that's what we're doing here. So get byte argb gets the first one, check comma B. So these are jumps into the ROM. Get the numeric value, that's basically the same as this. Check for a comma, get a number, check for a comma, get a number, et cetera, et cetera. So this is truncated just because the rest of, this function is quite long. So with that, I can demonstrate it working. All right, there we go. Let's see. So this is the loader, and it does the loading of the code image and puts it up in high memory. So let's run the loader. And now it's in there. So now we have commands like vwidth 64. Let's go back, unpatch vwidth, vpalette. So let's change green, that's slot 0. I don't know, to a purplish color. Let's go back to stock defaults. Let's turn on scan lines. Whoops. So anyway, so the ROM patch worked. It's taking full advantage of the 64K that's in the machine now. We're patching and unpatching and all that good stuff. So let me let's go back to this. Okay, so, all right, so where can I go from here, right? Some of the questions I get around this are things like, gee, could this be done without 64K RAM? Well, sure it can, right? But the advantage of doing it with 64K RAM is you can use that upper memory region and you don't have to get into the area that you would be using for your basic program or whatever. You can reserve space down in that lower 32K region by using clear, right? And that's commonly the way it's done. Could this be put in a ROM, EEPROM, EEPROM? Well, not in its current form. I think we probably could, right? Could put it as a disk cartridge ROM, initialize, switch everything into all RAM mode. It would still require a 64K system in order to patch and unpatch, the 64-column text mode. But there are other examples of this. ADOS is one from back in the day that you could customize to your heart's content, right, and mail off the disk back to the guy that made this, and he would burn a ROM for you, and then you could drop that in your disk controller, and you'd have a custom ROM, exactly to your liking. And then, last but not least, I want to thank some of the folks that pointed me in the right direction when I started on this. Some of the guys on Discord pointed me at Unraveled books, which I already knew about and was looking at, but I didn't quite know where to start. And there's actually a really excellent series of Rainbow Magazine articles called Cooking with CoCo from 1984 that was really awesome, and I'll have a copy of that at my table. And then, Pierre with his CMOC example, and of course the other Unraveled books. So anyway, that was probably a bit of a drink from a fire hose. Are there any questions? Yeah.
There's no way you could have gotten enough, because you connect into the video chip, that doesn't have enough for you to patch the stuff from your whatever you're doing.
So think about it this way: the video chip socket, it has a limited view of what's going on in the rest of the system. It's hidden behind a latch, first of all. So it can't see arbitrary accesses that the CPU is doing. And there's only 5 pins, the GM bits, AG, so alpha and graphics, and CSS, the color set select. Those 5 pins are driven by a PIA, a register. And so that's basically the only kind of direct control from the CPU, 1 5-bit register. So, that's one advantage, if you can connect to the cartridge port, like Peter's doing, you can actually monitor your address and data lines, and then you can do all sorts of cool stuff. Any other questions? All right, thanks everybody.